Hey there, Calc 3 folks, back here with another lecture in our study of the vector calculus. In this section, we are kind of finishing up that section on the linear integral, where we're going to look at linear integrals now within the vector field, right? And what we open with is just by noting that along with applying this integral operator, what we understand now as the linear integral operator, to some scalar value function little f, right? This linear operator, right? This what kind of represents, or what represents the process of integrating over some curve, right? Can be applied over a curve C in the vector field f bar, right? Resulting in a couple of different interpretations we're going to see. Those being what we call, or what I'm going to call, the flow of f bar, and what we also define as what's known as the flux of f bar over that curve C, when C is defined what we say parametrically. All right. Now, what do I mean by all that? Well, let's consider a generic illustration of a vector field, right, and a curve C occurring within that vector field, right? Consider in general the parametric curve C contained in two-dimensional space occurring within the vector field f bar, also contained in two-dimensional space, right? Note this illustration right here, right? Here we have our vector field f, and in that vector field f we have this parametric curve C. By parametric, it does have an orientation within this system, right? And we can see here the forward orientation is moving us in this direction along that curve, right? What we can take note of in this illustration, I do summarize down below, right? And what we say is, note, at every location, x1, y1, located along this curve here, within this vector field f bar, right, some of that vector field, right, at x1, y1, moves in the direction of what we think of as being forward tangential behavior at C, right, or I should say on C, at that location x1, y1, which is denoted by vector t bar, right? And this measurement over curve C quantifies to what we call the flow of f bar over C. So if I just start here with this first bit of note, is that if we're at some location on this curve in this vector field, right, this vector field is going to be occurring at that particular location. And at that particular location, some of the field here, which I have represented with this blue vector here, moves in the direction tangential to the curve, tangential to what we think of as being forward orientation along that curve. All right? That quantity, right, over this entire curve C, the quantity of the field that moves in the direction of the curve, right, quantifies to what we call the flow of the curve over C, right? Or I should say the flow of the field f bar over curve C, right? How much of the field moves in the direction of the curve, right, is what we call the flow of the field over that curve C, right? Whereas at every single location in that field, you do have, well, I should say at every single location on this curve C, the field is occurring at those locations. So if we consider being at the location again x1, y1, right, some of the field at that location is actually occurring in what we say is the normal direction, right, to the curve, right? The quantity of the field that is moving in the normal direction to this curve quantifies to what we call the flux of the field over C. All right? What we note here is, whereas some of that field moves in the direction normal in behavior to C, right? This is what we call maybe this vector capital N, right? The principal unit normal vector in our illustration up above, right? And this measurement over curve C, like we said, quantifies to this flux of F bar over C, right? As for the calculation of flow and flux, right, what we see are what we call linear integrations occurring within vector fields, right? We see some specific what we call linear integrals of the vector field. And these are going to appear in a couple of theorems here. The first theorem for the case of flow. Right? This theorem here. So as for the flow here, we can see we suppose that vector F, this vector field F bar, contained an n-dimensional space, and this can be a calculation that is made in n dimensions, right? Describes a vector field function over a continuous curve C, also in that n-dimensional space, where C is defined parametrically by the vector valued function r bar of t for values of that parameter t from A to B, right? So assume we have a setup very similar to what we have illustrated above here, right? We have this curve C occurring within this vector field F bar, where C is this continuous curve that we can think of as behaving parametrically, meaning it has this orientation to it, right? And defined in terms of the parameter t, right? The flow of that field F bar over curve C is given by the linear integral calculation that we say here, right? It is this integral, linear integral over that curve C that happens with respect to the arc length parameter S, right? Where the integrand is just the dot product of the field function with the description of tangential behavior, right? Remember, dot product, folks, gives us projections, the quantity or the vectors described by projections here. And what we are considering doing in this calculation is calculating the projection of the vector field F bar onto this tangential direction at every single location along the curve C here. And when we sum up all those infinite values for the projection of vector F onto this tangential vector, what we would say is the dot product, or that measurement given by the dot product, which actually describes the quantity that's moving in this direction for F bar, the magnitude of it in a sense, that's moving in that direction. When we sum that up for all values along this curve C, we are getting a measurement of flow, right? The flow of the field F on C. And how do we perform an infinite summation? Well, we understand infinite summations are the process of integration here. We're going to infinitely sum all the dot products of the field on the tangential vector along our curve with respect to the arc length of that curve. And how we go about calculating that is what we define here on the right-hand side. All right? We do have to consider having our curve C defined parametrically by r bar of t. That is where it all begins. Where if we have it defined parametrically in terms of r bar of t is going to tell us that description in terms of what we would interpret as that n-dimensional curve, right? Where the first component is x at t, the second component is called y at t, the third component is called z at t, and so forth. Right? Where what we're able to do with x at t, y at t, and z at t, we are able to go up into our vector description of the field, which is itself a vector description of f in terms of, the x component in terms of some function of x and y, the y component in terms of some function of x, y, and z, the components of the, or the dimensions of the space, right? And that could go on dot, 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 right, in either case. Right? And that vector field be described by some n-dimensional vector, right, description, where what we're able to do with these descriptions of x, y, z, and so forth is go into our descriptions of little f, little g, and so forth, and replace all the x, y's, and z's with their understanding here in terms of t. What that will prepare for us, right? What that will prepare for us is going to be this quantity we call f bar at t. Right? And with r bar at t, I can find its first derivative and form that into a dot product with that quantity of the field, that description of the field written in terms of the parameter t. That dot product is going to form the integrand in this calculation, and what it will form is a scalar valued function that we're going to integrate with respect to that parameter of t. Right? Now, in this understanding, this vector t bar is what we call the unit tangent vector to that curve C at the value of little t, at the value of the parameter. And note, with a little bit of theory, we can show that this calculation is true, right? This calculation is this dot product in terms of t given here, right? By noting that ds dt is equal to the magnitude of r bar prime at t, which does imply ds is equal to that magnitude of r bar prime at t dt. And furthermore, since t bar at t is equal to r bar prime at t divided by that magnitude, when I substitute this quantity for t bar into this statement and this quantity for ds into this statement, I prepare this argument here where these magnitudes in the statement will cancel, right? And I'll be left with here just the linear integral over curve C that now happens with respect to parameter t on an integrand described by f bar dotted with r bar prime at t, where certainly we are going to have to think of defining f bar in terms of t to get through our calculation and have t describe the bounds on our integration. All right? But this is what we see happening in the theory in terms of the linear integration. All right? This description of flow does have some more specific understanding when we consider curve C defining the motion of an object subject to a force field described by f bar, right? If C is describing the location of an object in space at time t, right, subject to the forces of field f bar, the amount of work done by the field f bar to move that object over that curve or that path described by curve C is given by the flow of the field calculation. It is given by this linear integration that we've defined above, right? It is given by this calculation, right? If this represents the motion of an object in space over time t, right, the linear integral given by this calculation here for the dot product of f bar with the unit tangent vector t bar and integrated with respect to arc length yields the work done by the field f bar to move that object. All right? That's one formal interpretation, more specific to the idea of motion, right? We can even go further with that and note if C happens to define what we call a smooth closed curve, if it defines some sort of looping curve in space that cycles over itself, if it's something like a circle or an elliptical path, right, that moves through space and comes back to its beginning and cycles around, right, over parameters of t, right? What we get when we perform that linear integral calculation, we understand as the flow, it becomes formally known as what we call the circulation of f bar on curve C. Right? If this curve C loops back on itself in the vector field and we perform the flow calculation on curve C over this field, right? Or I should say, if we perform the flow calculation for f bar on curve C that is a smooth closed curve, what we're describing is the circulation of the field f bar on our curve C. All right? So we do have, in addition to understanding it just as a measurement we call flow, we understand it, or can also interpret it as work under these assumptions, and we can interpret it as circulation under these assumptions. Right? Let's look at a specific example. Right? We might consider the case of calculating the flow of this vector field in two-dimensional space described by y comma negative x squared over this curve C defined by r bar of t, the parametric curve t comma t squared for t in that closed interval from 0 to 2. Right? Both the vector field f bar and curve C occurring in two-dimensional space. What is the flow of the curve, or the vector field f bar on this curve C? Well, let's see here. In this case, as I noted, it all starts with r bar of t, right? For an r bar of t equal to t comma t squared, the first derivative of r bar prime of t, is going to be given by 1 comma 2t. It is just the derivative of each of these components. And when we think about redefining f in terms of t, right, we can replace the x in our description of f with t. This x replaced with t becomes negative t squared. And we can replace our description of y in terms of t by replacing y with t squared. So we replace this y with t squared seen here, and that prepares for us f bar of t. Now with f bar of t and r bar prime of t, when I go to calculate the linear integral describing flow here of the field over that curve C, this calculation here, I am just going to be integrating from a to b, 0 to 2, what's going to be the dot product of this vector in terms of t with this vector in terms of t, and integrating that all with respect to t from a to b. Now in this case, t is going to go from 0 to 2 again, right? F bar is t comma negative t squared, r bar prime of t is 1 comma 2t, and their dot product is as follows. All right? But keep in mind the dot product is just the sum of the product, the sum for the product of the components of the vector, right? I'm going to take t squared times 1 and add that to negative t squared times 2t. And when I do that, I obtain this argument seen here. That is t squared minus 2t cubed. That is the dot product of these two vectors. Right? And we are just going to integrate that now from 0 to 2 with respect to t. And we take note, this is just a polynomial scalar valued function in terms of t. And we follow some fundamental rules in that integration here. So the integrals we calculate, folks, are, they can be tricky at times, but they are setting themselves up as scalar integration of single integrals that we are, or should be quite familiar with all the way back to our Calc 1 days. Right? And our techniques developed back in Calc 2. Right? What we do notice here, right, if we take the integral of t squared, that is 1/3 t cubed. The integral of negative 2t cubed is negative 1/2 t to the 4th. Increase those powers by 1 and divide by those new powers. And 2 divided by 4 is negative 1/2 in this case, and negative 2, right? And if we evaluate that now across the bounds from 0 to 2, it's 0, it all zeroes away. But at 2, we get 8/3 minus 8, which simplifies to negative 16/3. Now, You might be asking yourself, how is it that I get a flow measurement that is negative? Right? What does it mean to have a flow measurement that's negative? Right? If we look at the graph, that might help us understand, right, this negative flow measurement. Right? Here's the illustration of what we are calculating the linear integral of, right? What we're calculating the flow of. We're calculating the flow of this vector field seen here, right? F bar over this parametric curve seen here, where to begin with, we might note the orientation of this curve. The orientation of the curve says it starts down here at 0, 0, right? Because that's where t would be 0, and if we plug 0 into this description for r bar of t, that would put us at 0, 0, right? And we're going to consider this curve forming all the way up till t is 2. Now at 2, that would put us at 2, 4 in location, right? So this is the curve C starting here at t equal to 0 and going all the way up to this location where t would equal 2, right? And it's flowing in its forward orientation in this direction as highlighted by that arrow, right? Now notice how the field behaves, right, as it passes through that curve. As the field passes through that curve, some of the field can be described as moving in the tangential direction to the curve, meaning the direction that's considered moving forward on the curve, and some of the field can be described as moving orthogonal to that curve or normal to that curve. Now, if you take note as to how this field is behaving tangential to the curve, which is what we calculate when we make this flow calculation, notice it doesn't appear that very much of the field is moving in the forward direction. In fact, it looks like the field is actually moving in the opposite of, or some of the field is moving in the opposite direction of what is forward orientation along our curve. For instance, at this location right here, we can see the field is actually moving down and to the right, where the curve is actually moving up and to the right, where there is going to be some opposition of the field to that forward motion. In a sense, the field is not really contributing to any flow along the curve. We might say it's impeding some of the flow along that curve, right? How much is it impeding the flow along the curve? Well, that's what we just calculated right here. This negative 16/3 is the measurement of how much the field is working against the forward motion along that curve. If that curve was considered a path of motion for some object, subject to this being some force field, right, you can see that the force field does not help at all in moving that object along that path. That force field would actually work against the forward motion along that path. And how much it would work against is it would contribute to negative 16/3 of the work done to move that object forward, meaning that it's actually taking or causing us to have to contribute 16/3 more units of work or more Newton meters of work to move this object forward than if we were to move this object without the force field affecting the motion. All right? Now, this cannot be interpreted, though, in terms of circulation, because this is not a loop, right, folks? So we can interpret this as a flow, or if this is motion in space, we can interpret that as a work. And here we just set it up as a flow calculation. How much of the field is moving forward in the forward motion with the curve? Well, not much at all, right? In fact, overall, over this entire length of the curve from t equals 0 to t equal to 2, it actually impedes the curve in its forward motion, right? By this measurement, we might say is negative 16/3, all right? We take note below here, right? Now, again, folks, that is what we call flow. Let's look at the theorem now for flux, all right? as we began to highlight, flux is going to describe, right, when we think about the flux of F bar over C, it's how much of the field is moving orthogonal to the curve, or what we say is normal to the curve. All right? In a sense, it's some of the field moves with the curve and some of the field moves across the curve. How much of the field is moving across the curve? That is a measurement of fluctuation of the field across the curve, or what we just summarize as flux of the field over the curve, right, or across the curve, right? This theorem looks a little similar in its setup, but I do point out to begin with, flux does exist in n-dimensional space, but flux across a line only is considered in a two-dimensional system. When we move to 3 dimensions, what we have to start to consider is not flux across a line, but what we start to think about there is flux across a surface, right? And as we move to 4 dimensions, the idea of flux doesn't become flux across a surface, the idea becomes flux across a hypersurface. Right? So in terms of flux can be calculated in n-dimensional space, but when we focus on calculating flux in 2-dimensional space, right, it only occurs across a curve in 2 dimensions. Right? So what we do see here is a setup very specific to 2-dimensional space, whereas flow can occur in n dimensions. Right? And we didn't have as specific of a setup. All right, so you'll notice that's kind of what has added to some of the complexity of this definition. So to begin with, what we assume is we have that vector field function described as this 2-dimensional vector field in terms of the locations x and y. All right, and that is occurring over this curve C, right, over what we might say here is a continuous curve C. Right? Also contained in 2-dimensional space, where C is again defined parametrically by this description R bar at T, where in 2-dimensional space here, again C being in 2 dimensions is described by the parametric equation x at t comma y at t. Right? And this is all for values at t, the parameter in the interval from A to B. Well, the flux of the field over C is then given by this linear integral calculation. Right? This does match up with the book a little more. I've just used little n bar instead of big N in this calculation. Right? Little n bar is just a vector that is normal to the curve. It doesn't necessarily have to be what we call a principal unit normal vector. Right? Where n bar at t equal to this is, well, let me go back here. Let me say it this way. Is a normal vector to R bar, or really maybe we should just say to C, right, at parameter t, right, such that if you take the unit tangent vector and you cross it with, right, the unit tangent vector of C at t, and you cross it with of C at t, right, consistent with the orientation, and you cross it with k bar, the standard unit vector that points off in the 3-dimensional space, you obtain this description of this normal vector, where we are going to be integrating how much of the field projects onto that normal vector. All right? As we had noted, we are back here in our initial setup. Some of the field at this location moves in this direction, the direction of the principal unit normal vector in this setup. How much moves in this direction? Well, that depends upon, well, that can be measured, I should say, by projecting F bar onto N bar and measuring the magnitude of that projection. And the measurement for the magnitude of that projection is the dot product, right, of f bar with n bar. Now, it doesn't have to be the principal unit normal vector. You can project into either direction of normality. But normality is formally going to have an understanding specific to the, what we would say is maybe the orientation of the curve. All right. I might have to hold on a sec. All right, folks, I'm back. I had to get in there a little bit on the understanding of what direction this is going to actually describe, right? And what direction it actually describes based upon this understanding does follow the right-handed rule, where if I was to place my hand on top of the plane involving the unit tangent vector, or I should say including the unit tangent vector and that that standard unit normal vector pointing up along the positive z-axis, if I was going to place my right hand in that plane, right, and curl my fingers from T bar to K bar, my thumb will point in the direction of little n bar here, right? Which, if we want to interpret that, we might say the direction of n bar falls to the right of the curve C, right? It would fall on what you would think of as being your right-hand side when moving in the direction of forward orientation along that curve, right? If we were to be on this curve here and we were to move in forward orientation, what would be on the right half of the curve would be this side of the curve, right? And n bar would be projecting orthogonally off our curve in this direction, all right? It would follow what we would call the right-handed rule again, right? It would be on the right of C, right, as you move forward along the curve C, right? Now, you will notice this is just another scalar valued integration. You are going to approach it just as you had for the case of flow, right? You are going to, with r bar at t, it all starts with r bar at t, you are going to calculate the first derivative of r bar at t. Those values for the first derivative are going to be used in here for y prime at t and x prime at t. You are going to redefine f in terms of t using these values of x at t and y at t. F at t is going to be this factor here in the first term, and g at t will be this factor here found in the second term of the integrand. And your integrand is just going to be the difference of the products of these two individual functions, or I should really say these four functions. The f and the t coming from our vector field description in terms of t, and the x prime at t, y prime at t coming from the measurement of r bar, or the description of r bar prime at t in terms of t, right? And when this integrand is formed, this integrand is just going to be a scalar valued function that you're going to integrate with respect to t, right, across those bounds from a to b, all right? Now, we do have an additional interpretation here, right, that we can go a little further with C, and that is the case of what we might call it, if it is the case that C is a smooth closed parametric curve orientated in the, what we would say is counterclockwise direction, right, then the flux of f bar, the flux of the vector field over that curve C describes what we call the outward flux of f bar. All right? If it is a smooth curve C and it's orientated parametrically in the counterclockwise direction, when you calculate flux, what you're calculating is the, what we could more formally distinguish as the outward flux of that field. All right? It's how much of the field is pointing outward from the curve. How much of that field is moving from inside the curve to outside the curve in a sense. All right? We might consider calculating the outward flux for this curve here, seen here, right? Consider the outward flux of the vector field f bar seen here, given by y comma negative 2x. That would describe this vector field seen right here, over the closed curve C, right? Over the closed curve C, illustrated by this vector valued function r bar of t, this elliptical description of a path. This what we would note as a smooth closed curve, right? That is occurring for values of t in the interval from 0 to 2 pi. All right? This field, right, could be generating an outward flux on this curve C as we move around the curve C in this counterclockwise direction. And the total outward flux at every single point along this curve is given by that flux calculation. Now, as I noted, it all starts with r bar of t. R bar of t is going to be used to define f, your field function in terms of t. This y will be replaced with 3 sine t. This value of x will be replaced with 2 cosine t. And then as noted above in the calculation, not only are you going to need little f and little g in terms of t, the descriptions of the field, right, for little f of x comma y and little g of x comma y, you're going to need the first derivatives of x and y seen here in your vector description of the curve. Well, the first derivative of r of t, 2 cosine t, 3 sine t, well, the derivative of 2 cosine t is negative 2 sine t, and the derivative of 3 cosine t is positive 3 cosine t. All right? And we make note of all this below as we begin our calculation. All right? We might note, in the case of this f bar and this r of t, right? You can note here I did redefine f of t in terms of y being 3 sine t and x being x being 2 cosine t, which would produce negative 4 cosine t in our description of f of t. And the first derivative of r bar prime of t is that negative 2 sine t, 3 cosine t. All right? Where if I now take this quantity times this quantity, I get 9 sine t cosine t, and subtract from it this quantity times this quantity, I would be subtracting positive 8 sine t cosine t. And my flux calculation in this case, right? So my flux calculation in this case, so the outward flux of f bar over curve C is the following value, right? Is this value right here, right? Which is again going to be that integration that was set up in the above theorem, right? Where we had noted it is just going to be the integrand built by 9 sine t cosine t minus 8 sine t cosine t, which simplifies to an integrand given by sine t cosine t, where we are going to integrate with respect to t over those bounds from 0 to 2 pi. Now, right? Now, how do we integrate the sine t cosine t? Well, this does go back to some Calc 2 methods, we might say, or this is pretty simple u substitution. You may have even made note of this back at the end of Calc 1, and that is if you just let u equal sine t, du will be the cosine t dt, and the sine of t cosine t dt can turn into the statement u du. Replacing cosine t dt with du, and replacing the sine of t with u, you get u du. Now, notice what happens in the bounds. If I take this bound to t and I plug it into the sine of 0 is 0, whereas I get the exact same thing at 2 pi. Sine of 2 pi is also 0. And what do we know about an integral that occurs across bounds that are equivalent? Well, it doesn't matter what this argument is, the integrand is, right? That value always results in the value of 0. Right? So what does that tell us? The outward flux, right? Well, it doesn't, it has no value here. It is null in value. Note, this result implies there is no outward flux of the field, F bar, across the boundary defined by C. Right? And actually, if we go back and we take note of that illustration, we should be able to see that. Right? Curve C moves in this direction, right? Field F cycles around in this direction, right? If we look at the edges of curve C in this direction, what you will notice is not much of the field as it moves in the opposite direction is actually moving across the curve C. It might be moving, it looks like, very parallel in its behavior to curve C at all these different locations. If it does happen to move across curve C a little bit in its path, that is balanced by moving back into curve C somewhere else. So that in terms of the total flux, right, of the field here over this curve C, the total outward flux, that would all balance and become the value is 0, the value of a null outward flux in the end. All right? Whereas if I was to try to, I think, go back and calculate a circulation in this case, the circulation would certainly be equivalent, right? And what we might note here is if the curve C flows in the counterclockwise direction and the field F here appears to flow in the clockwise direction, we might think about how much of the field is moving in the direction of C at any point along C. Well, I think it'd be easy to argue is not much of the field. In fact, it looks like a lot of the field is opposing the direction of C rather readily. And we would probably get a rather large calculation in the negative direction for that circulation. You might consider calculating that calculation on your own and seeing that result. But in this case, for outward flux, we do get 0 as a measurement for the outward flux. All right? Folks, this is, in our book, in our current book, this is section 17.2 that's looking at linear integration. I did give you some notes a couple of videos ago looking at linear integrals of scalar valued functions. What we've now come back is looked at linear integrals over curve C's of scalar value functions. Now we've looked at linear integrals over curve C's in vector fields, right? And there are two common calculations of a linear integral that can occur over a curve C in a vector field described by F bar. And those two common calculations we can encounter are the cases for flow, which could be interpreted as work or circulation based upon those conditions for work and circulation, and can be another common case is this calculation for flux, or in this specific case, the case for outward flux. All right. In terms of the linear integrals that you can calculate that occur over a curve C in a vector field F bar, these are the two common calculations. These are the calculations that our book is presenting to us in this section on linear integrals when it gets into that calculation of vector fields, of the linear integrals over vector fields. All right. So, folks, this does wrap up this section of notes. Where we're going to head to is we are going to skip a little bit over conservative vector fields and spend some time getting into Green's theorem, talk a little bit about surface integrals, and then get into Stokes and divergence theorem, where, as you may have noted or as I had just noted back in our study of flux, flux is a concept that occurs in two-dimensional space over a curve C, and in three-dimensional space is a calculation that occurs over a surface, and is going to require a surface integral to calculate. Right? So what we are going to do is we are going to introduce surface integrals later here in the chapter to allow us to calculate flux over those surfaces. That flux being given by what we call our what am I thinking there? Oh, our surface integral. Right? That flux of a surface across a surface integral. Oh, and that's Stokes' theorem. I do believe that Stokes' theorem is related to those ideas. All right. So, folks, that is where we're heading with all this. I hope you're hanging in there. I hope you're watching these videos and keeping on top of all this. We are almost done. The last few sections, although they're going to cover some rather higher level concepts in the vector calculus, right? In the book in terms of calculus, I hope that you're going to find that they're not too difficult to pick up on with the time that remains. These calculations, folks, these do have some heavy theorem behind them, right? They do have some heavy theory behind this calculation for flow or the other calculation for flux here, right? But the calculations you actually are going to be setting up, these linear integral calculations, are going to be scalar valued calculations, right? Calculations of integration that happen just in one dimension, right? With respect to some parameter t, and they have a very specific formula that you can prepare with the parts that you are given, right? And with that said, I will stop there, but we'll be back in the next video to kind of continue on with these ideas looking at Green's theorem. Green's theorem is going to present us with some unique and special cases for calculating these flux and flow calculations. And actually, we're going to be looking at the specific cases of closed curves and looking at calculating circulation and outward flux, right, with some more convenient integration. Right, actually pumping it up a notch and not looking at it as necessarily an integration over a line, but actually starting to look at it as an integration over a region, right, a two-dimensional region. And as that would imply, we're going to be looking at calculating circulation and outward flux using some double integration, which is setting us up for those surface integrals and that understanding of a surface integral, folks. So, that's where I will finish this video, and I hope you're hanging in there, and I'll see y'all next time.